let's have a look at the final video in our three-part series on surface area and volume, which today is going to be volume, guys. Okay, what is volume? Well, the volume of a three-dimensional figure is the amount of space it takes up. It's as simple as that. And the units we use for volume are cubic millimeters, cubic centimeters, and cubic meters in this video. That's right, volume just equals space, yeah? Okay, we're going to talk about prisms now. The volume of any solid with a uniform cross-sectional area, which is a prism, that's what the definition of a prism is, by the way, is given by the formula V equals A, which is that cross-sectional area, that uniform cross-sectional area, times H. So A is a cross-sectional or base, if you like, area, and H is the height of the solid. Now, the height simply means the dimension, the linear dimension, the side length, which is perpendicular to the solid's cross-sectional base area, okay? This is a physical height, depth, or length, okay? That's what that is. You'll see that in a moment as I show you some. Prisms are the most recognizable solids because they have uniform cross-sectional areas and they're very easy to pick. A prism is a solid shape with identical opposite ends and they're joined by straight edges forming a congruent or identical cross section. That's what I've been saying. So in some cases, yes, you can develop a special formula from this generalized formula V equals A times H, as we'll see in a moment, alright? So there's a prism, okay? Now, can you see a cross section or one of the sides, one of the outside sides of that prism, which is the same all the way through it to the other end? Well, you certainly can. You can see the front. If you slice that all the way backwards to the back of it, you'd get the same identical cross section as the front and the back. Yes, or you could do it from the sides, from the left hand side to the right hand side. They're all identical cross sections, and even from the top right down to the bottom, if you sliced it in that way, you would get identical cross sections again. So it's definitely a prism. And there's three ways that you can basically get your identical cross sections happening, isn't there? I've just done the one way just to show you. That's cross-sectional area there, which is uniform from the bottom all the way to the top. And that is the height. That is the height which is moving away from that base at right angles to it. Okay, so that is the height we would use in that case. Okay, moves away from the base in a perpendicular direction from it. Okay, so the volume of this thing would be this cross-sectional area here times this height. Yeah, there it is. You got it? Very good. Now let's apply that newfound knowledge to these situations here. For that cube, I could say they're both prisms. I could basically say for the cube, there's my cross-sectional area, there's my height. Okay, so and you just get that formula there by multiplying that cross-sectional area, which happens to be L squared, by the height, which is also L, which gives you L cubed for this cube. For this situation down here, same idea. We've got the cross-sectional area there, for example, and you could multiply that by that height there, and you'd get this formula here for the volume of that rectangular prism. Now, what about this cylinder and this triangular shape here? They're both prisms. They're both prisms. For the cylinder, you could say, okay, that's my cross-section there, my cross-sectional area. If I multiply that by H, I will get the volume of that cylinder. And you know that the cross-sectional area of this circle is just pi r squared. So it's pi r squared times H, which is what you get there. Okay? What about this one here? Well, that cross-section there is uniform all the way from there right down there to the very end at the back. It's always the same shape if you slice that with a knife, yes? All the way along that ridge there, you get the same shaped triangle. So that is our uniform cross section. Now, what is the area of that? Well, it's a triangle, isn't it? So the area will be half base length times vertical height, and then multiply that by capital H, and you get the volume of the triangular prism, yeah? So there you go that way, and that's what you get. Yes, okay. Find the volumes of the following shapes. Well, it's just plug and chug, guys. Plug and chug, you know what to do, don't you? For this one, it's a prism. Therefore, there's the cross-sectional area, there's the height. So therefore, the volume is pi r squared for the circle times h for the height, which is pi times 14 squared times 20, which is apparently 12,315.04 cubic centimetres. My goodness, that's a lot, isn't it? And what about for this one over here? Well, have you worked out where the identical cross-section is? Yes, it is the triangular face here. What's the area of the triangular face? It's half base times height, which means half of 4 times 5, and if you multiply that by the length along here, you'll get the volume. Yeah, so there's the cross-section, there's the height, and the volume is the cross-sectional area times the height because it's a prism. And first of all, we need the cross-sectional area, which is just the area of a triangle, isn't it? There it is. So we get half 4 times 5, and we get 10 square centimetres out of that. And if we multiply that 10 square centimetres by the height, or the length along this ridge, which happens to be 10, we will get the volume is 100 cubic centimetres. Yeah, very good. Now, what's this one? What effect will doubling each of the side lengths of a cube have on its volume in comparison to the original shape? Oh, we've got to double each side length. All right, look, draw a picture. A picture's worth 1,000 words, guys. So let's do this one, and then we'll do the second one in a minute. There's a cube, and I've called the side lengths L. The length, the width, and the height all L. So what's the volume of it? L times L times L. So there it goes, L cubed. And now look at this one. This is twice as big in the length, in the width, and in the height. Okay, so what's the volume of this big one? It's the same formula, but it's just 2L times 2L times 2L, which gets us 8L cubed, and therefore this figure is 8 times as big as this one, isn't it? So therefore, increasing the side length by a factor of 2 increases the volume by a factor of 2 cubed, or 8 times. Okay, get that? Great. Well, we better do B now. Over the screen we go. Now, for B, what effect will halving the radius and doubling the height of the cylinder have on its volume? Well, we'll do it exactly the same way in comparison to the original shape. So let's draw an original shape. We'll call the radius R, we'll call the height H. So the volume of that thing is the cross-sectional, area, which is the circle, the uniform cross-section, pi r squared times little h. Yeah, there it is. Now here's the other strange-looking beast. What we've done is we've doubled the height of the cylinder, and we've halved the radius. So let's use those figures. This will be r over 2 now compared to r over there. This will be 2h compared to h over there. Let's apply the formula. So it'll be pi times r over 2 all squared times 2h, which gets us that. And what does that get us? Oh, pi r squared h over 2. So you can now see that this is exactly half of this one. Okay, so that must be the effect. So we've halved the volume of the original shape, as you can see. V1 was pi r squared h over here. V2 was pi r squared h over 2. Yeah, this is this one here, V2. All right, very good, excellent job. Now we're going to do spheres. Okay, the volume of a sphere, this is a new one for you probably. If we have a radius of r, the formula for the volume of a sphere, V, is 4 over 3 pi r cubed. And guys and gals, these are definitely not prisms. Okay, so that's a special formula that you have to use just exclusively for spheres. Okay. Worked example. Find the volume of a sphere of radius 9 centimetres and give your answer correct to 1 decimal place. Well, I can see a plug and chug coming, can't you? R is going to be 9, so therefore it'll be mighty fine. We get V is 4 over 3 times pi times 9 cubed, which comes to a lot. 3053.6 cubic centimetres. Okay, that's to 1 decimal place, isn't it? So we're right, aren't we? Great. well, what other pleasures have we got in store? NB, goodness, what is this? Oh yes, a sphere is not a prism. I already said that, Mr. Computer, but thank you for reminding me. It does not have a uniform cross-section. No, it does not. If you sliced, go and get an orange or something like that, or a grapefruit, and you slice it, parallel slices all the way through, you'll see what I mean. They're definitely not the same cross-sectional area. Okay, pyramids now. Pyramids are special beasties. Basically, they're not prisms either, are they? Goodness, there's no way you could get a uniform cross-section by slicing that with parallel slices in any particular way. No way. So I'll just give you the formula for the volume of a pyramid. It's a new one again, probably. It's 1/3 of the cross-sectional area of the base times the vertical height, okay? So this is the base here. So if you did the area there, okay, and you multiplied that by that vertical height up there to the apex, to the topmost point, okay, using a line which is perpendicular to the base, going right up there to the apex, you'll get the volume. 1/3 of the area of the base times the perpendicular height is the volume of a pyramid. Whether it's a square-based pyramid or, yes, whether it's a square-based pyramid or whether it's a cone, which is just a round circular-based pyramid. Okay, same formula, except that the area of the base in this case is pi r squared, where r is the radius of this circle. Okay, so for a cone, it's 1/3 pi r squared h, where h is the vertical height again. Okay, all right, that's good. Let's do a work example now. This is another plug and chug situation for us. Let's do the cone first. Now, it's pi 8 squared times 10, all divided by 3. Here it comes. Yes, that's what it is. Now, what does that come to? 670.21 cubic centimetres for the volume of that cone. Yes? Now, what about this square-based pyramid here? It'll be 1/3 of the area of the base, which is 1/3 of 8 times 8, times vertical height of 12. So that's what we get, and that comes to 256 exactly cubic centimetres. Okay, how are you feeling? Yes? Very good. You're getting something out of it? That's great. Alright, composite figures now. These are just the figures which we've got several known shapes joined together to make a joined up or composite shape. Okay, what you do is you work out the volume of each smaller solid component separately, and then you add them up. Okay, the volume of the composite solid is calculated by just summing the volumes of each of the smaller solid components. Okay, you knew that, didn't you? Okay, here's one. Now, see, that's a composite shape. That's got a cube there, and it's got a pyramid there. Yes, doesn't it? So we could work out the volume of this cube. Then we can work out the volume of the pyramid, both of which will be very easy. Then we just add them up. Yeah, a cube and a pyramid. Okay, the volume of the cube, which is a prism, is the cross-sectional area, the uniform cross-sectional area times the height. So we can pick any cross-sectional area here. We can do either the front, or which is the same as the back, or we can pick the left-hand side, which is the same as the right-hand side, or we can pick the top, which is the same as the bottom. It really doesn't matter for our uniform cross-section. So it'd be 3 times 3 for the area of the cross-sectional bit, and times 3, which gets us 3 times 3 times 3, which gets us 3 cubed, which is 27 cubic metres this time. Now, let's do the pyramid. No, that's not a prism. No way, Jose. So the formula for the, let's do the volume of that will be 1/3 of the area of the base times the vertical height, which would be 1/3 of 3 squared, 3 squared being the base, times that height there, which is 1.5 metres. So we get that, and we get, what do we get? 9/2 cubic metres. Yes, so now we've got to add them up together. Total volume is 27 from the cube plus 9/2 for the pyramid, which gets us 63/2. Okay, 63/2 cubic metres. Yes, great. Now this is the last little bit that we need to really concentrate on here. This is capacity, which refers to the amount of liquid which will fill up or fit in a three-dimensional figure. And The thing is, guys, we use slightly different units for liquid measure, okay? We're used to using milliliters for, say, a can of soft drink, liters for, say, a bottle of milk or orange juice or something, and kiloliters for what you get on your water bill. You don't pay the water bill, probably, if you're watching this, but I do, okay? And they tell me how many kiloliters I've used. Kilo means 1,000, so that's thousands of liters. That's what that means. This one here means milliliter, or 1,000th of a litre, okay? Yeah, it's fascinating, isn't it? So, okay, here they come. Volume and capacity are fundamentally related, yes. Well, they're basically the same thing. We just use different units, that's all. Different looking units. So, one cubic centimetre, this is what I really need you to know. 1 cubic centimetre is the same as 1 millilitre. They are the same thing. So, when you buy a 375 ml can of soft drink, it's really 375 cubic centimetres. Same thing. Same thing. 375 cubic centimetres of space, which is filled up by 375 millilitres of whatever is in the liquid in the drink, right? Get that? Very good. Now, a litre, 1 litre, is 1,000 cubic centimetres, or if you like, 1,000 millilitres, right? Okay? Yes, you get that? And lastly, 1 kilolitre, 1,000 litres, 1 kilolitre is the same as a cubic metre. That's all. That's what I need you to be able to readily translate between those measures, okay? Those measures. They're all really measures of volume, but the liquid volume we tend to use millilitres, litres and kilolitres, okay? Yeah. Okay, let's go for an example now. It's a fish tank. Find the capacity, which means the volume to fill up in litres, a rectangular aquarium, which is 50 centimetres long, 30 centimetres wide and 40 centimetres high. And let's draw it. There it is. 50 centimetres long, 30 centimetres wide and 40 centimetres high. So what is the volume of this? Well, it's a prism, guys. It is definitely a prism. So it's pick a cross-sectional area which is uniform throughout its perpendicular length. Okay, so let's you can pick. You can do the front, you can do the side, or you can do the top. It really doesn't matter for your cross-section because they're uniform all the way through. Times the height. So what did I pick? I picked the base as the cross-sectional area, which would be 50 times 30, and I multiplied that by the perpendicular height from there, which is this 40, okay? So that gets me 50 times 30 times 40, which is a big number. 60,000. 60,000 cubic centimetres. Now, I've got to convert this into, what have I got to convert it into? Litres, okay? A liquid measure, right? Now, do you remember how many cubic centimetres there are in a litre? Well, it's the same as how many millilitres there are in a litre, because a cubic centimetre is the same as a millilitre. Therefore, we've got 1,000 millilitres or cubic centimetres in a litre. So if we divide that number there, that's 60,000 by 1,000, because there's 1,000 of these little gremlins in every 1 litre, then we convert it to litres. So we'll get 60 litres. I think that's the end of the show. Oh no, we've got to remember, okay? A remember. All right, let's go through these. The volume of a three-dimensional figure is the amount of space it takes up. Well, we know that. Volumes are measured in cubic units. We know that. Volume of a prism is the cross-sectional, uniform cross-sectional area times the height perpendicular to that. Yes. The height of a prism is, what is that? Oh yeah, that's the perpendicular dimension which I was just saying up there. Perpendicular to its cross-section, its uniform cross-section. Spheres, 4 over 3 pi r cubed. Cones, 1/3 of the area of the base, being 1/3 of pi r squared times the vertical height. Pyramids in general, 1/3 of the area of the base times the perpendicular height. And the capacity of a three-dimensional figure is the amount of liquid which will fit into that figure. Yes, it is. And the relationship between the volume of a solid and the capacity, which is the amount of liquid which will fill in it, or that it can hold, is 1 cubic centimetre is 1 milliliter. 1,000 of them fit into a litre, and 1,000 litres, being a kilolitre, is exactly 1 cubic metre. My goodness. Hope you got something out of that. Yes, you're a star and you'll go far, but you'll need to practice them. Practice them and get good at them and get familiar with these things. Volumes are great fun and interesting to do. So, all the best to you and we'll see you soon. Bye-bye for now.